Hey guys, Mr. Palmer here with a problem involving thermodynamics as usual. Please try and go through this. This is a long problem. It should take you somewhere around 20-25 minutes to complete this. Hopefully on the smaller side. Make sure that you're showing all of your work and following through. You'll see that there's a couple of other things mixed in with this problem. This is one of two thermodynamics problems I'm going to do based around the same equation, and what I'm going to try to do is just break these up into two shorter videos, two small parts for each one. So first, let's tackle the first part of this, probably like parts A and B, and then we'll run through the rest. This one is about the production of iron. We're taking iron oxide, which is hematite, and we're reacting it with some carbon monoxide to generate iron and carbon dioxide. You're given a delta H. So the first part of this problem, you'll see, starts out with giving you a mass of hematite and asking you for the mass of iron. So this is a straightforward mass-mass problem using the balanced chemical equation. In this case, you're given a number of kilograms for which you're going to have to convert into grams. So 54.62 or 0.26 kilograms is the mass that's giving you of Fe2O3. First things first, kilograms to grams. One is 1,000 grams. We're going to convert to moles, so we've got to find the molar mass of the iron oxide. That's going to be 159.7 grams per mole. From the balanced chemical equation, we have a 1 to 2 ratio for the mass to mass. So every 1 mole of iron oxide is going to give us 2 moles of iron. And then finally, we need the mass of iron. The atomic mass of iron is 55.85. That's what's on your AP periodic table. For every 1 mole, this is our grams of iron. We multiply that through, you get 37,951 grams. Probably that's 4 sig figs, so 37,950 or 37.950 or just 95 kilograms is also fine. Any way you want to do this, I'd say this is a 2-point problem. One is probably for getting the correct mole calculation of your iron oxide, and another point for solving all the way through. You really could just, alternatively do one of these where you take the 54.26 kilograms and you just go back and look at the structure of this. So, every 1 iron oxide's got 2 irons in it. So you could really just say 2 irons, what's that going to be? 111.7 kilograms of iron in every 1 iron oxide, which we've calculated to be 159.7 kilograms of Fe2O3. As long as we're using that mass ratio to find the mass of iron that we could get, that also works for 2 points. As long as you have your justification in there. Let's look at part B. Part B asks us to find an enthalpy change when this mass of hematite is going to be converted. So this is our amount of the hematite. I'm going to, again, start with that quantity. And if you'll see, I put in here, right, not only to balance the chemical equation, the enthalpy is our delta H. So for this reaction, right, every 1 iron oxide that gets reacted, every 1 hematite, is going to give me negative 23.44 kilojoules. It's going to be released. So we're going to have to convert these kilograms into grams. We're going to have to take those kilograms and convert to moles. So we've got, what was our molar mass? 159.7 grams in every 1 mole. Now you could stop there and calculate the number of moles. I think it's 339.8. You could stop. That's your moles of iron oxide in the problem. And then multiply that by the delta H. Or we could keep going through here and saying, okay, every 1 mole of iron oxide, right? For my balanced equation, that's what's in here. Every 1 mole is going to give me 23.44 kilojoules released. If you multiply that all the way out, you get negative 7964. So that's the amount of energy that's going to be released when this happens. So when it's saying enthalpy change, you really need to have the sign on there as well to indicate that this is going to be a negative change, right? You're not going to get full credit. And this, I'd probably figure like a 2 point as well, calculating your moles of iron, right? And you get another point for the correct setup for multiplying by the delta H for this case. Okay? I'll come back and I'll finish the rest of this in part 2.